We're going to start a new unit today. We're going to talk about circular motion. We've finished talking about two-dimensional motion. The two units leading up to two-dimensional motion, if you remember, were balanced forces and unbalanced forces. So we're going to talk about a special kind of motion now, circular motion, which is specifically, just like it sounds, motion in a perfect circle. Here are some examples of things that move in a circle. We got a bowling ball that moves in a circle. Remember when you guys were out in a hallway and you were hitting the bowling ball with a mallet and you were making it go in a circle? I could put a ball on the end of a string and I could swing it over my head in a circle, so it was swinging in a perfect circle over my head with the tension on the string pulling on it. You could drive your car in a parking lot in a perfect circle, right? Roller coaster cars sometimes go upside down in a loop-to-loop in a perfect circle. And if you think about planets orbiting the sun, they go in a circle. So these are all examples of objects, and we're going to pretend they're like point-like objects that are moving in a circle. When I say point-like objects, I mean that the object doesn't have any specific size or shape. It's like all its mass is concentrated at a single point. So even though a bowling ball has an actual size and shape, we're going to pretend that the size and the shape don't affect its motion at all. And we can model it like a single tiny little point of mass, just like all these other things. So my question that I might want to ask is, are these things moving with constant velocity if their speed is constant? And you might think, okay, constant velocity, doesn't that mean that their speed is constant? Well, what you have to remember is that velocity is a vector quantity. What does a vector quantity mean? Remember from back earlier in the year, vectors have two things. They have a magnitude or a size, and they also have a direction. So when I say a size when it comes to velocity, the size of the velocity is the speed, how big the number is, right? 20 meters per second versus 10 meters per second. That's the magnitude of the velocity. 20 has a larger magnitude than 10, so that's a greater magnitude of velocity. It's a larger speed. But velocity also has a direction. The other kind of quantity, remember, is a scalar, and that doesn't have a direction. So like temperature, mass, time, those are things that are scalars that don't have a direction. Speed doesn't have a direction because that's just the scalar version of velocity. Your speedometer in your car doesn't tell you which direction you're going. It just says you're going 20 miles an hour. So velocity being a vector, if the direction changes, if the direction of the velocity changes, that means that velocity is changing, even with constant speed. So if you go in a circle at 10 meters per second because your direction's changing every instant, that means that the velocity is changing, even with constant speed. So we're going to draw a force diagram to further understand what's going on here. So let's pretend we're doing that activity that we did in the hallway where you were asked to hit a bowling ball with a mallet in a circle. And if you remember, you guys probably started out trying to hit the bowling ball along the path like this. And if you did that, if you tried to do it along the desired circular path, what you found is the ball would roll wide. It wouldn't actually follow a circular path. It would go somewhere out here. So as you developed the skill and figured out how to get it to go in a circle, you kept having to hit it directly towards the center. So if you go back and open up that worksheet at the beginning of the balanced forces unit, and where you had to draw a picture how you hit it, you had to point your mallet directly towards the center of the circle every time you hit the bowling ball. So if I draw a force diagram of that bowling ball, here I'm looking down at it from a top view. Here I'm going to look at it from the side. So this is a side view right here. And I draw a force diagram at the two different positions. Here at position B, I guess, and I don't know, we'll call this another position over here. But this is a side view. You've got the normal force acting up, you've got the Earth's force on the ball, and you've got the mallet force on the ball. So you've got force of the floor on the ball, normal force, force of the Earth on the ball, those balance each other out. Then you've got this unbalanced force of the mallet on the ball when it's in position B. When it's in this position over here, the mallet is hitting it towards the center of the circle there. That's this force right here. So both of these are unbalanced force diagrams, and in both cases, the unbalanced force is directed towards the center of the circle. In one case, it's directly right here, and in this case, it's directly left, but they're both pointed towards the center of the circle. Okay, does the net force, which we sometimes call the unbalanced force, always point towards the center of the circle for objects moving in a circular path at constant speed? Let's look at a couple other examples. Here's the roller coaster car that's going around a loop-to-loop. When it's at this top point right here, it's got two forces acting on it. It's got the Earth's force down. We always call that Fg. And it also has the normal force of the track acting on it down. So I've got a normal force and the force of gravity acting downward on this object. So actually, we would have two forces acting down. So definitely the F net is towards the center of the circle here. If you think about the Earth orbiting the sun, going around a circle here all the way around the sun, at any point you want to pick, the force that the sun is exerting on the Earth is a gravitational force directed directly at the center of the sun. That's how the gravitational force works. So the Earth is always pulling you down towards the center of the Earth. The sun always pulls the Earth towards the center of itself. So in both those cases, you can see that clearly the net force is directed towards the center. So this seems to be a common thing, that the net force, let me write that differently here. So there it says the net force is always pointed towards the center of the circle for an object that's moving in circular motion at constant speed. So it doesn't matter what position the object is around the circle. Picture the Earth anywhere around the sun. That net force, the only force, the gravitational force, is directed towards the center of the sun. Since the net force is in that direction, according to Newton's second law, if the net force is in a certain direction, that means the object has to accelerate in that same direction. Remember, Newton's second law says that acceleration is always in the same direction as the unbalanced force. So Newton's first law said an object that's at rest is going to stay at rest. An object in motion is going to stay in motion in a straight line at constant speed. It's not going to change directions all by itself, but as soon as an outside and external net force acts on it, it's going to accelerate in the direction of that net force or that unbalanced force. Doesn't mean it's going to move in that direction, but it's going to accelerate in that direction. So since an object is going to accelerate in that direction, that means that the velocity has to be changing also. So it's got to be a delta v, because remember, acceleration is defined as a change in velocity over a time interval. So the velocity is changing, the car is accelerating, even though the length of that vector, see, here's a car going around in a circle. Notice how the length of that vector doesn't change. So it's constant. Whatever the speed this car is going, 20 meters per second, it's going to stay constant speed, but at every instant it points in a new direction. So constant speed, still accelerating. So we know the object's velocity is changing. We know it's accelerating. We know the acceleration has to be in the direction of the unbalanced force. So that must mean the acceleration is also towards the center of the circle. Here's how we can kind of prove that with vectors. We're going to pretend we've got a little ball rolling around a circle here. It's right at the top of the circle. We're going to consider the time when it starts there and it ends over here. So this is the initial moment. That's the final moment. It's going around in a circle. At the center point, it's pointed directly to the left there. It's going around the circle this way. So it's got an initial velocity vector this way. It's got a final velocity vector that way. So this will be VI. It'll be VF. The vectors are the same length because it's moving at the same speed, but they point in different directions. They're always tangent to the path of the object as it goes around a circle. So just pretend this is a ball that's being rolled in a circle around maybe a track or something like that that's causing it to go in a circle. Well, remember that the change in velocity, the delta V, is final minus initial. So if I wanted to figure out what direction the delta V points, it'd be like adding a negative. So VF plus a negative VI. Well, with vectors, a negative just means you flip the vector around. So I would take this VI vector right here, and I would flip it around so it would be the same length but in the opposite direction. So remember how we add vectors? When we're adding one vector to another, we do it tip to tail. So I'm going to add this vector to the opposite of the first one, which is this one. I'm going to add them tip to tail. I'll do it over here on the left. So I've got VF plus a negative VI, sorry, VF. A negative VI goes like that. And then the sum of those two is from the tail of the first to the tip of the last. So there's the delta V that results. And notice how that is straight down towards the center of the circle. So there's the delta V right there. Points down towards the center, that's the same direction as the acceleration. So to sum up, we can say since acceleration is change in velocity over change in time, and we just proved that the change in velocity is pointing towards the center of the circle, that this vector, the acceleration vector, is also going to point towards the center of the circle, which is consistent with the unbalanced force pointing towards the center of the circle. So on Wednesday, we're going to do some activities in class and hopefully reinforce this a little bit with you. See you Wednesday. Have a nice day off or a nice distance learning day.